Hi everybody, this is Mechanical Engineering by Hand, and in this video I'll be talking about drag force. So, as you probably know, drag force is on an object moving through a fluid or a gas. So if we have a ball falling through the air, there's going to be a force acting up on the ball from the air, and the equation for drag force is force in pounds is equal to a drag coefficient times the specific weight of the air times the area of the object, and that would be the area as you look at the object as it is hitting the fluid or the gas, times the velocity squared divided by 2g. And if you have density, in other words, in the English system, that would be slugs per cubic foot, then this is the equation. So let's look at this example. Let's say we have a steel ball. And it's got a 1-inch diameter. And let's say it's falling at 100 feet per second. So the specific weight of air at standard conditions is 0.075 pounds per foot cubed. And the area of this object as it is hitting the air for a sphere, it's going to be the same no matter how you look at it, but it's best to consider the area as it's hitting the gas or the fluid. So that would just be the area of the circle with 1-inch diameter, and we need that in square feet, so that would be 0.0055 square feet. And then our velocity is 100 feet per second. And now we need to find the drag coefficient. And we need to calculate the Reynolds number to do that. So let's look at the Reynolds number. That is diameter times velocity over kinematic viscosity of the air. And so that will be 1/12 for the diameter times our velocity, and then the kinematic viscosity of air at standard conditions is 16 times 10 to the -5 feet squared per second. And so this equals 52,000. Okay, now we need to look at a drag coefficient chart, and the best one that I have is in this book, of all places, Piping Handbook, and it's the best one I have because I have others, but they're printed smaller and so they're more difficult to read. And this one has more lines which represent different shapes. So this line is for flat plates, circular discs, cylinders here, and then on the bottom we have spheres, which is this dashed line. And so we need to find the Reynolds number, which is here on the bottom, and then just read the drag coefficient over here on the left. So our Reynolds number was 52,000. This is 10,000, and this is 100,000, so it's going to be between there. And a handy way to find that is to read a log scale like that is to take the log of 5.2, and that equals 0.72. So we're going to be 72% of the way over. So about right here. And then I go up to that line for spheres, and it is 0.5 for the drag coefficient. So we have 0.5, and then our drag force will be the 0.5 times 0.075 times the area times the velocity squared over 2g. So that equals 0.032 pounds. So over here there's going to be a 0.032 pound force acting up on the steel ball. All right, now if we want to use the drag force to determine the terminal velocity, we can do that. The terminal velocity is when the drag force equals the weight. So we'll have a force pulling the ball down equal to its weight, or mass times gravity, and then an equal force acting up from the drag force. And at that point, the steel ball will stop picking up velocity and it will just continue to fall at that velocity, which is its terminal velocity. So let's look at that. We've got a steel ball with a 1-inch diameter. And we want to know the velocity, and the drag force is going to be equal to the weight. So we need to find the weight. So the first thing is the volume. Volume for a sphere is 4/3 pi r cubed. And so in cubic inches, that would be 0.524 inches cubed. And then for steel, that is typically taken as 0.283 pounds per inch cubed. So we just multiply these two and we get a weight of 0.148 pounds. Okay, so that is also going to be our drag force. So we'll go over here to the drag force equation. The force, which we know, is 0.148, and then we'll need to find the drag coefficient times the specific weight of the air times the area of this object times velocity squared divided by 2g, which is 64.4. Okay, now we have two unknowns here, the drag coefficient and the velocity. So what we'll do is just assume one of these things, and then we'll recheck our result to make sure it makes sense. If it doesn't make sense, then we'll make an adjustment. And we'll keep adjusting it until it makes sense. So it's an iterative process. Okay, so I'm just going to assume that the Reynolds number is pretty high, and so our drag coefficient is going to be here at 0.2. So let me erase that and I'll put 0.2. Okay, and this is equal, or sorry, when we what we would do then is solve for velocity. So solving for velocity, we get 340 feet per second. Okay, so now we want to check the Reynolds number to make sure that makes sense. So the Reynolds number for the 340 is dV over kinematic viscosity. So we have 1/12 times the velocity, 340, divided by the 16 times 10 to the negative fifth. So that is 177,000. Okay, and then using this log calculation of 1.77, we get 0.25. So going back to our drag coefficient chart, 177,000 is going to be between 100,000 and a million and a quarter of the way over. So that would be about right there. We go up and we see that the drag coefficient is about 0.5. And we assumed that it would be 0.2, so we need to make an adjustment for that. So the drag force will still be 0.148, and then we have our new drag coefficient and specific weight of the air, area of the object, and we'll solve for velocity again and divide by 2g. So velocity is 215 feet per second. Okay, now we can check that by checking the Reynolds number for 215. So that's going to be 1/12 for the diameter times 215 over the kinematic viscosity of air. And that equals 112,000. So just going back to our chart again, 112,000 would be real close to this 100,000 line, and we go up and see that the the drag coefficient is 0.5. So that is all good, that checks out. So I would say the terminal velocity is 215 feet per second. And that is a couple of examples on drag force. Thank you for watching.